Hi guys, this lesson is about pedigree analysis, and the first pedigree that we're going to look at is one from a family that has hemophilia, which is a recessive X-linked trait. And with hemophilia as a disorder, this is basically a blood clotting disorder where individuals usually have a very hard time clotting after a cut, and can usually bleed pretty heavily even just after very small cuts. And even carriers, some carriers will show signs of this disorder either by taking a little bit longer to clot themselves or just being very easy to bruise. It's very common in the older royal lines where in order to try to keep the royal lines pure, they would inbreed within the family. So there were a lot of different mutations that were going on, but also inheritance of the mutated gene. So let's just take a look at a couple of the different symbols that we've got here so you know what you're looking for. First of all, you're going to see a lot of boxes and circles. All right, so here's a box, here's a circle. The line in between shows that this couple here is married, and if they have a line stemming off of them with offspring, these would be their offspring where the line directly goes into another box or another circle. These circles are female. That's the sign for the female. Boxes will always be male. Okay. You may have a pedigree where it shows a diamond shape. That's usually because the sex is unknown of the offspring, so we don't really know the sex if that occurs during a pedigree. Now, some other things to keep in mind when you're reading a pedigree is that if the box or the circle, and I'm just going to use a box for right now, is shaded in, and we see these a couple of times here, here, and here, so there's 3 individuals with shaded boxes, and they all happen to be male, that usually means that that individual is what we call affected. Now, if the box or the circle is not shaded in, that means one of 2 things. Usually in the simpler pedigrees, they're either unaffected or what we call normal, or they may be carriers of the defective gene. In simpler pedigrees, you don't really know. However, in more complicated pedigrees, they might look something like this if they're a carrier. If this is a male carrier, they would have part of its box shaded. If it was a female carrier, it would be partly shaded as well. Okay, and that would just mean that they are carriers. All right, so let's get to the actual pedigree. In a recessive X-linked pedigree, it's very easy to kind of follow in a pedigree who is affected, who's not, and you can figure out the genotypes by just taking and starting off with the affected individuals and working up. One other thing that I'd like to point out are these Roman numerals on the side. These Roman numerals indicate the generation, this being the oldest generation, this being the newest generation. And usually in questions you might see, you know, find the genotype for individual 1 dash, let's say 4. Okay. In this case, there are only 2 individuals, so let's change this to a 2. So what they're saying is this would be generation 2. And then you would count from the left, 1, 2, 3, 4. And this is the individual that they want you to figure out the genotype for. Now, one other thing that you need to be aware of when you're trying to figure out genotypes for a pedigree is that individuals that tend to marry into the family, such as this person here, as you'll see that they do not have a direct link to somebody else in the family as far as being offspring. They come right into the family, marry in. Unless otherwise stated or otherwise determined by an affected, their affected offspring, you should assume that they come into the family normal. for whether you're dealing with a dominant pedigree or a recessive pedigree, they're always going to be normal unless the pedigree states otherwise or you figure out otherwise, which we'll find out in a second. All right, so now that we've kind of got the generals out of the way, let's start by taking a look at this individual right here. This would be 4-1, and we're going to take a look at him. Because this is X-linked, there's a couple different ways that you can write this. You can write it just like you would normally do. Remember, this is recessive, so the recessive alleles will be lowercase if this individual is affected by it, which this person is. So we're just going to use a little a for that. And he's a male, so this is kind of what his genotype would look like, and he is definitely affected. So obviously the dad above would have given him this allele to make him male. However, the mom gave him this one, but the mom is unaffected. However, she did have this recessive allele. So if she is unaffected, she must be a carrier, because in order to be affected, you have to have the recessive genotype. So not only did we figure out the affected male, but we also figured out the father and the mother's genotype. That being, the mother is a carrier, so she looks like this, capital A, little a, and dad looks normal. Dad, I'm going to write him down here, big A, because he's unaffected, and a Y. All right, so now we need to follow where these genes are coming from. So obviously this guy married in, which would make sense. He's normal. Sometimes, however, you find out that they might be carriers if this was a female, and so on. So that's why you need to start usually with the affected and usually at the lower level. So let's follow these genes up. We know that this individual, this mother, is a carrier. So where did she get her genes from? Well, let's take a look. Her parents are also unaffected. However, this individual does have that recessive gene. She must have gotten it somewhere. The other way you can figure this out at this point too is we have another affected individual, and this individual is male again. So again, they're going to have basically what looks like the same genotype. This gives us a clue as to dad here. Dad had to only be able to give this guy a Y. Okay, so, and he's unaffected, so his genotype kind of looks like this, A. I'm actually going to blow this up a little bit. Unaffected, so his X chromosome is unaffected, and he had to give this Y chromosome to have a son. So where did this individual get affected? Well, got that recessive gene from mommy, so mommy has to be, and is unaffected as well, so has to be a carrier. So mommy is going to have capital A. Her other X chromosome is going to be a little a. Again, if you look all the way over here, there's another male. So again, his genotype is going to be X with that recessive allele and the Y. Again, if you look where his parents, if you just follow the line, we can figure out that dad is obviously unaffected and had to have given the Y. So his genotype is going to be X, big A, Y, because he was able to give that Y. And now we know who is basically handing off these genetic disorders to the whole family. That would be mom. So that X, and she's unaffected, so she's got a big A, but this is the one that counts right here. So this allele right here is the one that's being passed down to all these other individuals. Now, one other thing that you should be looking at are individuals off on the side here. Obviously, if you're looking at this woman here, she is free and clear, it seems, because she looks like she's unaffected. Again, this is a more simplified pedigree, so we don't know if she's a carrier or not. So you would have to look at her offspring. Well, none of her 4 offspring are affected. So it's pretty reasonable to suspect that she has a dominant Oops. That is obviously not dominant. She is a dominant genotype. Okay, and has obviously passed that along. And again, as I said before, always assume that these guys are normal. So let's just move down here. I want to show you, I got this from this website right here, and you can always look them up. But this is a really good example of a dominant autosomal disease. The individuals that are affected would be in blue. The individuals that are either carriers, or I'm sorry, they can't be carriers if they have that dominance. So they could be heterozygous for a genotype, in which case they would have that dominant allele, which would make them affected. Or they could be homozygous dominant. So they could have this, let's just use A's again. They could have the heterozygous genotype, which means that they would still be affected. Or they could be the homozygous dominant genotype, which means they would still be affected. So the only way in a dominant pedigree to be unaffected, and remember, in a dominant pedigree there's, again, no carriers, the only way to be unaffected is to have that recessive genotype. So all the individuals that you see here that are not shaded in have this recessive genotype, this homozygous recessive genotype. All the other individuals that you see here in blue are either going to be heterozygous or homozygous dominant, and you can kind of figure that out as you go along. So I hope this helps. Thanks.